Hello, in this video we're looking at the indefinite integral and net change. So just as a reminder, if f is an antiderivative of lowercase f, then f plus any constant, that's going to be an antiderivative of f as well. And the new thing here, it's something that we've talked about in the past, but we've got a new notation, new name. So the collection of all these functions, the collection of all antiderivatives is called the indefinite integral of f. So for example, we've shown previously that capital F x equals x squared, that's an antiderivative of lowercase f, of x being 2x. And the way you check that is the derivative of x squared is 2x, so capital F prime equals lowercase f. So in this new notation with this new name, we'd say the indefinite integral of 2x is x squared plus c, so the collection of all the antiderivatives. So this process of evaluating an indefinite integral is important, and one of the main things is we need to find antiderivatives to use the fundamental theorem. That's a big result for us. It helps us compute definite integrals. Well, what do you need? You need an antiderivative. So just as a reminder, the difference between these two things, for indefinite integrals, we're looking at a family of functions. It's just a set. For the definite integral, it's going to be a number. So far, all the rules that we have for indefinite integrals, well, they're exactly the same rules we had for finding antiderivatives. They're just those that arise as kind of reversing the processes, or reversing the differentiation process, so the reversals of the rules that we know with derivatives. So, for example, we know that the derivative of tangent is secant squared, and so that tells us that the indefinite integral of secant squared is tangent. So it's very limited so far. Soon enough, like I said here in the note, I'll learn more techniques for finding these, but right now it's very limited with what we can do. So the other thing I want to mention here is net change. And if capital F is an antiderivative of lowercase f, then capital F prime equals f. And by the fundamental theorem, since this is just f, fundamental theorem, as we've been calling it part 2, says that if f is continuous, then the definite integral from a to b of lowercase f is capital F of b minus capital F of a. So the antiderivative, any antiderivative, evaluated at the endpoints. Now, if we think of the integrand as capital F prime, that's certainly true by the fundamental theorem. And our interpretation is the integral of the rate of change is going to be the net, or if you like, overall change. So the final value b, the initial value a, and the difference, that's the net change. So it's a pretty cool thing. So you know something about this. You know the instantaneous rate of change. You can learn something about the net change if you apply a definite integral. Classic example, looking at velocity, that's the rate of change of position. So this would be just the velocity there. And the definite integral of that is going to be the change in position, the net change in position. So a couple things we want to be careful with. We want to distinguish between displacement and distance. Displacement is the net change, and distance is the total change. And just kind of a silly example, if I go 3 steps forward and if I go 1 step back, then the displacement, or the net change, is 2 steps in the forward direction, while the total distance traveled would be 4 steps, 3 forward plus the 1 back, so 4 overall. And in calculus terms, what that means is for displacement, we would compute the definite integral of velocity. That's the net change in position. Whereas for the total distance traveled, we would look at the definite integral of the absolute value of the velocity. And this idea is going to be the same for all sorts of applications. The idea being net change versus total change. So for the net change, we just integrate the function. For the total change, we're going to integrate the absolute value of the function.